functions or the properties of a system. I guess we did that.
So no.
Hey, we
Oh,
didn't talk
maybe
about.
we have forgotten. So you
We,
just summarize it and then let's continue.
okay, so we made mention that when we talk about extensive um, properties, these are the properties that do not really um, change the entire thing of the system, right? And we also all the other dependent variables. So when you talk about intensive, they are the independent variables of a system. So they said extensive, that is proportional to system size. So the size of the system is related to extensive, and those that are not independent to the system size are intensive. So, for example, if you are talking about extensive, you can talk about the volume, you can talk about the mass and energy, because those things are proportional to the system size. For example, if you take a glass of water, that glass of water has a defined volume and it has a defined mass. Okay, and these properties, that is the volume and the mass, are proportional to the system size, because if you reduce this, the mass of this water, you realize the volume will also decrease. So, irrespective of whatever the properties, whenever there's a change in it, it affects the system size. Okay, but when you talk about the intensive, that one, it does not really change the size the size of the system. So, for example, if you have a glass of water, right, and we increase the temperature, it doesn't really affect the mass or the volume of the water. It's still the same mass and the same volume. Likewise, if you increase the pressure, the same thing. It doesn't really change the size of the system. I hope we are making sense here.
Yes, sir.
Okay.
So, Doc, sir,
Yes.
yes, if you increase the temperature, it doesn't really change the system.
Yes.
Due to expansion, when the volume of the water or the glass change.
Come again.
I'm saying that you said for the other system, when you increase the temperature,
Yes.
it doesn't really change the system.
Yes.
So I'm saying what happens to expansion? If the glass expands, the volume will increase, and then the temperature of the liquid also may cause the volume to increase due to expansion
Okay. For
or
this,
evaporation.
yes, for these properties,
Yeah.
we are not talking about it in terms of a wide increase of the temperature or the pressure, because you also know that when you increase the temperature so much, the water will evaporate.
Yeah.
Yeah, but we are talking about the things that can be detected quasi-static equilibrium. That's all that.
Okay.
So things that can be detected as we change from one phase to another phase, not that drastic, but if there is increase in a little amount of those properties, can we really determine what is happening in the system?
Okay. All right. Thank you.
So that is that. Then we go to the mathematical function of state. So when you are trying to relate the mathematical function of state to a system, it can be really put in the function form. Then the function at which we are looking at, or the state at which we are looking at, will be in bracket to determine that state. Okay. So let's look at what we have here. They said function of state can be explained by letting the state of a system be described by parameters x, and the x is in bracket of those parameters that are changing, and let the function f of x be some function of states. Then if the system parameters change from si to sf, where the si is the initial and sf is the final, then the change in the function is given by this. That the change in function is changing from the initial to the final of the function f, which you also know from your level 100 or your mass that if you have in the system, it's given by the final minus the initial. That will give you the change. right? I guess you know that already.
Yes, sir.
Yes, so that is what I've been done here. So assuming um, we have a system, okay, and the system initially it was having a temperature of, let's say, 20 degrees Celsius. And after some time, the temperature changes to, let's say, 70 degrees Celsius. So when we want to find the change in temperature from the first state to the final state, it's a matter of changing subtracting the initial temperature for the final temperature. And that's what has been represented over here. Okay. Now the quantity, the F is an extract differential because it depends on the endpoints SI and SF. Yes. Because we are trying to find the difference between the initial and the final. By contrast, a quantity which is represented by inexact differential is not a function of state. So when we are trying to find a difference in a function of which you don't give you the final and the initial, we say that differential is inexact differential of function, in a, in inexact differential of that function of state. Okay, because if we want to find the change in um, thermodynamic property of any system, we need to know the final and the initial. Because you can't say we are boiling water, we don't know the final destination of the water, whether it's going to be ice or it's going to evaporate, and you're asking me to find a change in state. It's not reasonable. Okay, so always when you are asked to do that, it means you have to know the starting point and the end point, and that two difference will give you the type of phase or the type of changes this thermodynamic function is going through. I hope I'm making sense.
Sir.
Okay. A general equation which connects functions of states is called equation of states. So the general equation which connects functions of states is called an equation of states. An example of equation of state is that for an ideal gas, which is the form PV is equal to nRT. So this is an example of equation of state. Okay. So with this, we have all the parameters in there that you take a critical look at where it's changing from and where it's ending. So for example, we can have an equation of state where we have the change in pressure, okay, or change in volume or change in temperature. And these are the three major intensive and extensive properties that we always deal with. Okay. To move on to the next session, we talked about the first law of thermodynamics. And I guess this one you know already. What is the first law of thermodynamics? Ideally, like anything that comes in mind. Any idea? Yes.
It talks about the total energy of a system, which has to do with the work done by the system and then the energy, quantity of energy within the system. If you sum that will give you the total internal energy or change in the total internal energy.
Yes.
Depends on the work done. One.
Yes. Yes.
Yes.
So when you talk about the first law, you try to relate the internal energy, the heat and the work done on the system.
Yes.
That's what the thermodynamics do. I guess we spoke about the zeroth law already.
Yes.
Yes.
Yes, please.
So the first law. So reading from it, they said the first law of thermodynamics states that energy is conserved and heat and work are both forms of energy. So energy is conserved. That one you know already. That in any system we have conservation of energy, but rather we can have energy being transformed from one state to another. That doesn't mean that the energy is not conserved. So basically talk about conservation of energy. And they said a system has internal energy U, which is the sum of the energy of all internal degrees of freedom that the system possesses. U is the function of state because it has a well-defined value for each equilibrium state of the system. We can change the internal energy of the system by heating it or by doing work on it. So we can change the internal energy of a system by either applying heat or extracting heat from the system or changing the internal energy. Okay. So if you have a system and want to change the internal energy, you can either heat the system or do work on the system. Doing work on the system, it means we are trying to um, um, reduce the quantity of heat energy in the system. Okay. The heat, that is Q, and work, W, are not functions of state since they concern the manner in which the energy is delivered to the system. So they said heat and work are not functions of states. They are not functions of states. Okay. Since they concern the manner in which energy is delivered to or extracted from the system. Why? Because it's a way at which we extract um, um, energy from a system. Okay, or we add energy to the system. So if you have a system and want to extract energy from that system or want to add energy to the system, that's what we talk about heat and work done. So with this, they are not functions of states. Okay. After the event of delivering energy to the system, you have no way of telling which of heat or work was added to or subtracted from the system by examining the system state. So let's look at the scenario. It said this is a special case of the law of conservation of energy that describes the processes in which only the internal energy U changes and only the energy transfers are by heat. That's Q and work. The change in internal energy of the system can be written as. So when you are looking for the change of internal energy, it's given by that's change in the internal energy is given by change in heat plus that of change in work. So if you add this to, you are going to get the internal energy. Okay. And when you do that and you get negative, it has its implications. And you do that and you get positive, it has its implications. Because it said one, either the work is done on the system or work is done by the system. So that should give you an idea. If you have negative, it has its implication. And if you have positive, it has its implication. Where the change in Q is the heat supplied to the system, and change in W is the work done on the system. Okay. Let's note that the convention, the Q is positive for heat supplied to the system. If change in Q is negative, heat is extracted from the system. So if the heat energy that you are dealing with is negative, it means we are extracting energy from the system. Or sorry, we are extracting heat from the system. And if change in W is positive for work done on the system. So when you have change in W, it means we are doing work on the system or work is done on the system. But if the work done is negative, then it means the system does work on its surroundings. If the W is negative, it means the system have done work on its surroundings. For differential equation, we can rewrite equation one as, so from here, we want to eliminate the change and do it in terms of differential. So that I have the U is equal to the Q plus the W. We've not changed anything because the rate of change is the same as differential expressions. So instead of the change inside, it just represented that by the differential expressions. Okay. So we have some thermodynamic conventions. As we said, if you do that and you get negative, what are the implications? And that's what I've been summarized over here. So the Q positive means heat supplied to the system, and when it's negative means heat is extracted from the system. And when we have W to be positive, it means work is done on the system. When it's negative, it means work is done by the system on its surroundings. Okay. Please, I hope it's going well. Or is there any questions or concerns?
Please, okay.
Okay. So we go to the next session, which is session 4, which also talks about some implications of this first law identities. So we can define the thermally isolated system as a system which cannot exchange heat with its surrounding. I think we also spoke about isolated system or a closed system. Did we?
Yes, sir. Yes, sir.
Okay. So isolated system is the same as a closed system, and in that system, there it has nothing to do with the surroundings. It has nothing to do with the surroundings. And both systems sometimes have a rigid or closed boundaries. So there's no exchange of anything within the system and the surroundings. Okay. We can define thermally isolated system as a system which cannot exchange heat with its surroundings. That is, the change in the heat is always equal to zero because there's no way there's going to be a transfer of heat from the system to the surroundings. So if we are going to stick by that, then it means our decay is equal to zero. And a system where there's no change in heat, what does it call that system? Adiabatic system. I hope you know that.
Yes, sir.
Okay. So in that case, you are talking about adiabatic system. So when you substitute that one in the general equation, first law of thermodynamic expression, which we have the U is equal to the Q plus the W. It means you have the U is equal to then the Q equal to 0 plus the W. And at the end of the day, you know that we have our du to be equal to the W. So for adiabatic process, okay, always the internal energy is the same as the work done. Always the internal energy is the same as the work done. Okay. So they said adiabatic processes are very important in engineering practices. Some common examples are the expansion of hot gases in an internally combustion engine, the liquefaction of gases in a cooling system, and the compression stroke in a diesel engine. Okay, so when you are talking about adiabatic processes, that are some of the applications or their properties. And in that cases, we don't have heat being part of the system. Rather, the internal energy is all converted to the work. Okay. And go to isothermal process. And in isothermal process, it always takes place at constant temperature. And if the temperature is constant, means our dT is equal to 0. Is that true?
Yes, sir.
Okay. If that's the case, then means we have our dT equals 0. Now, from the ideal gas expression, which we've done previously, we said the internal energy is given by CVdT. Okay. CVdT, where the CV is the specific heat of um, um, specific capacity of specific heat of capacity of at constant volume. At constant volume. Specific heat capacity at constant volume. That's why we have it at V. So when you see the V, it's at constant volume, and when you see P, it's at constant pressure. Okay. So if you have our internal energy to be the same as CVdT, and now dT is equal to 0, so it means the V is equal to what? 0. Are we good? Okay. So if that's the case, we have our du to be equal to 0. Again, substituting this in our general equation, that's the first law. We have du equals dq plus dw. Now the du is equal to 0. So that we have dq is equal to negative dw. And this also holds. Okay. So what of in a system where you have constant temperature or in isothermal temperature? It means the change in heat is the same as the change in work that is being done. But this time around, you remember when we went up there, you say when you get negative load, what does it mean? Work is done by the system on its surroundings. When you get W to be negative, work is done by the system on its surroundings. Okay. So we have our the W to be negative. So it means work is done by the system to its surrounding. So any energy that enters the system by heat is transferred out of the system by work. So when I'm talking about isothermal process, any energy that enters the system by heat is transferred out of the system by work. As a result, no change in the internal energy of the system occurs in an isothermal process. In that case, there's no change in internal energy of the system. Yeah. Then go to isobaric. And when we talk about isobaric, we are talking about constant pressure, right? So the values of the heat and the work are both usually non-zero. So the work done is simply given by, so you have W equals P into L. We know PV, right? Now V is changing from initial to final because that's a changing problem parameter in there. So they have P dV. So the dV here the dV here is the same as what is in the bracket here. Yeah. So the dV is the same as changing the volume we have over there. Okay. This is the work done in compressing a gas. So the final volume would be less than the initial, so a negative sign. The negative also sign ensures that the W on the system is always positive when the V is negative. For a gas being compressed for an isovolumetric process, because the volume does not change, the work is given as, because the volume does not change, we have W to be equal to 0, because there's no change in volume. There's no change in volume. Then we have our dU to be equal to the Q plus our dW. Now the dW is equal to 0 because here we have the dV to be 0. There's no change in volume, so everything here goes to 0. So that I have dU is equal to the Q. So in this process, we've been able to derive that one for the isobaric, isovolumetric. We have isothermal and adiabatic. I hope you are okay. Or there is any question? Any questions so far?
So please, can we try one example and then we continue?
One example as in
Like the exercises under it.
they did not give exercises under those sessions.
Okay.
Yes, so it's just about getting the concept. That's it. So maybe if the question will be asked on that, they'll ask you how does this or what that this they will say maybe state the first law. After stating it, they will ask you how does this equation changes in terms of isothermal process, isobaric process, or something. So
Okay.
note
So they will
that
just have to prove the this thing, the formula.
it's not about proving the formula because
Okay.
if you know the first law, which is du is equal to the Q plus W, and they say in isobaric isovolumetric process, what does the expression changes to? So you have to
Okay.
know that in isovolumetric process, the V is 0, the V is 0, and hence W is equal to 0. Then you just go ahead and put that there and substitute in the final expression, and you are good to go.
Okay, sir. Thank you.
All right. Please, any more questions? Okay. So move to the next one, which is heat capacity. Heat capacity. So as you said, we have heat capacity and we have specific heat capacity. I hope you've all forgotten that.
Yes, sir.
Okay. So heat capacity have to do with the amount of energy needed to change the temperature of a system by 1 degree Celsius. Okay, or 1 Kelvin. Okay. So applying it to a system can be of two ways. And now applying it to a system, you can apply it at a constant volume or at a constant pressure. And that's where you have the CV and CP. So either by making the volume of a gas to be fixed, that's we are making the volume constant, then we apply heat to it. And that is our CV. Okay, that's the I. And when we go to the II, that's we are putting constraints on the pressure of the gas to be fixed. So it means we are making the pressure fixed and we change the heat capacity of we change the heat of the system. and that we have our CP. Okay. Now we go to derivations of expressions of heat capacity. So in general, the internal energy will be a function of temperature and volume. So we can write U as U in terms of T and V. Okay, because you know the internal energy is U, and now we are trying to write the function in terms of the temperature and volume. Okay, hence a small change in U can be related to changes in the temperature and volume by. So here, what we are trying to say is that when you have a system, its internal energy can be changed by either changing the temperature of the system or changing the volume of the system. So when you have a system at which you are changing any of the parameters, you now have the expression as this. Please, I hope you are not confusing anyone or you are confused with the equation 12.
Go over to equation 12 again.
Is it?
Please go over on equation 12 again.
Okay. What I'm saying is now we have the internal energy to be this. And we said for internal energy of a system to be changed, the two major things that can change this internal energy is either temperature or volume. So if you have a system and we increase the temperature, it means you are trying to increase the internal energy of the system. Or when you have a system and we are either adding or reducing the volume of the temperature, the system, it means you are either decreasing the internal energy or increasing the internal energy. Okay, so we are trying to find a way of which, if we increase either the volume or the temperature of the system, what happens to the internal energy? Okay, so now we differentiate this whole function by keeping one of the parameters constant. So if you take the first one, we are differentiating the u with respect to the t, and with that case, we make our v constant. Please, do you understand it?
Yes, sir. You are following.
Okay, sir.
Then we go to the second set over here. So we're also differentiating u with respect to v, but at constant temperature. So we realize the subscript over here are telling us the parameter at which we are keeping constant. The subscript we are having here is telling us the parameter we are keeping it constant. So you have the u dt now at constant volume, and you have the u dv at constant or at temperature. So that at the end of the day, if we want to get back to our normal this expression, this dt can cancel this dt and you have our du, and this dv can cancel this dv and you have our du, and at the end of the day, it's the same as this. It's the function of t and v. I hope I'm making sense.
Yes, sir.
Okay.
Okay. Now, rearranging this, we can get back to this. Rearranging this can get back to this. Because you know, from here, you said the W is equal to negative P dV. Right. So here, we have this whole thing to be as the P dV. And this whole thing is the same as change in internal energy. I hope you're okay.
Yes, please.
Okay. Now they say substituting the u gives into equation 13. Now we are trying to substitute the du in the whole expression so that we have all of this over here, and we have our dq there, and we have our pdv. Are we okay? Now we know equation 13, right? This equation.
Sir,
Okay. With this
hello, sir.
equation. And the du we have here, we are substituting this dv, this du in this equation. So that I have our dq here. Now our du is the whole of what we are having as equation 12. Then plus the pdv. Are you okay?
Hello, sir.
Yes.
Yes. Can you go back to equation Okay, yes. If you look at equation from equation 9, there's a negative sign there.
Yes.
Yeah. So that negative sign, when you put it into equation 1 point, if you put it into equation 12, if you substitute for it in equation 12, then we can make the Q the subject. I think that's what they did there. That's why that one become positive.
Yes, here you
Yes.
realize the DQ is the same as the negative DW, right?
Yeah.
And
Yeah.
here we have negative here. So that negative cancel out this negative, giving us a
Okay.
positive PDV.
Okay.
Yes. So at the end of the day, we have base to be PDV instead of the negative, because the negative for that of the work done has cancelled that negative here, giving us positive. Okay. And now this is the DQ that you know to be equal to du plus PDV. And we are saying now the du is given by what we are saying in equation 12. So instead of writing du in equation 13, we substitute the equation 12 into the equation 13. So the du will be what? Du over dt at constant v dt, which is the first term, plus the du over dv at constant t dv, which is the second term. Then we add our last term, which is plus p dv. And that's what we are seeing in equation 14. Is it clear now?
Why is it positive now? Because it is negative dv, p dv.
Yes.
Why has it changed to positive?
Okay, that's what I'm saying over here. So realize here, we say the change in heat is equal to what? Negative dW. Right? Are you seeing that equation 8? Mr. Michael, are you following?
So what I am thinking is that
No. The W is also given by what? Negative PDV.
Okay.
So we are trying to substitute the negative PDV also here so that the negative will cancel the negative. Then you have PDV. Are you following now? We say our Q, the Q is equal to negative dW. Okay. And we say our W is also equal to negative PDV. So instead of the dW, let's substitute this parameter in here. So that I have the Q is equal to negative, then into bracket negative PDV. So that negative times negative becomes positive and have just PDV. Are you okay?
No, what you just said is not clear.
Okay. We said we have the change in heat is equal to negative dW. Okay. You're also saying that for isobaric process, we have W to be equal to negative PDV. Okay. Now this negative PDV is the same as the W, the change in work. Okay. So if that's the case, let's substitute the W you have here in here. So that I have the negative dW will be negative into bracket negative PDV.
Okay.
Yes. So if you are putting that one there, this negative will cancel the negative over here. Then we have PDV. So our change in or the Q will be equal to PDV.
And say, would that give a double in differentials?
No, it won't give the both differential. The W here
The
is the
degree, the
W.
degree is also a differential function.
Yes, the W here is the W. Because we are changing the volume. So it's W. Changing the work is equal to PVF minus VI.
Okay.
Yes.
Yeah. So let's go to equation 12. Equation 12.
Okay.
Yes. This equation 12.
Mm-hmm.
Yes. What I'm also thinking, what they did here was if we maintain the negative there and instead of the dv, the u, the v, at that dv, we can put it the negative p dv over there, and now try to make the q the subject. That will change the whole thing to positive.
That's also correct.
Yes.
But then because they established it from here, that's how I was going by that.
Okay.
Yes.
Okay.
Yes.
All right. Thank you.
You're welcome. So please, do you understand the equation 14 now?
Yes,
sir.
please.
Okay.
Yeah.
Okay. If that's the case, then from this expression, realize this last two terms. Okay. You can see this last two terms, they all have the v in there. So it means you can factorize the v out. So that if you factorize the v out, you have the u dv at constant t plus p. Then the dv will be outside. Are we good?
Yes.
Okay. Now, since we have this, we cannot, we want to have each term standing on its own. So it means we can divide through by what? Our dt. So if we divide through by dt, we have the q over dt equals now the u dt plus this whole term divided by dt. And that's what you are seeing in equation 15. Is that clear?
Yes, sir.
Okay, if that's clear, then we say at constant volume, the heat capacity is given as Cv is equal to the q dt, and that has been stated here already. Okay, that's this. Sorry, it's not giving the chance. Okay, so if that's the case, then it's given by the u over dt is at constant volume, which is the first term. Okay. Are we good?
Yes.
Okay.
Hello, sir.
Yes.
So please, why that was factorized? It's not very clear. Not
You
very
said?
clear. The part that the V was factorized out of the expression, that is 15, equation 14
Question 15.
to 14.
14, you said the part which one was factorized out.
How the V was factorized out of the expression, because if you go to 13, if you go to 13,
Mm-hmm.
if you go to 13, you have the V, the V is only one.
Yes.
That is the U, the T into bracket. Then you have the V, and that the V, from what we learn from factorization, it means that for you to be able to factorize the V, there's going to be common to both sides. Then you can factorize it out.
Mm-hmm.
But that the V was only attached to only one side.
Okay,
So
now
how it
hold
was?
on. Hold on. Do you understand to the equation 13?
Yes.
Okay. Now from equation 12, right? You are substituting equation 12 into equation 13, meaning the du in equation 13. This is the u. Okay. Instead of writing the du, you are substituting everything we have here. Is it clear now?
So that part is clear. It's only the
Okay.
factorization part.
So now we substitute that one over here. And now if you look at everything here, we have, let's try to take the square bracket out. Okay. It means we have the q equals to the u over the t at constant volume dt plus the u over the v at constant temperature dv plus p dv. Okay. Now, if that's the case, you realize the second term and the third term are having dv.
And
The
how about
second,
the first term that does not have, and the first term that does not have the V, how were you able to fight? Well, the first term does not have the V.
So we've expanded the whole thing, so it's not together again.
Okay, okay.
So,
Yeah, we are trying to expand it. So we take the square bracket off. So now everything is standing on its own. So this is one term, this is one term, this is also another term. And we realize the second term and the third term are having something in common, which is the DV.
so I
Okay,
think
that
the
is why the
factorization is
two
happening.
it's okay
Factorization is
now.
happening between the second and the third term.
Yes,
Yes, yes,
Yeah.
I now see. That is why we have the square bracket there. Okay.
yes. Okay. So here, so do you get the concept up to equation 16? Please, do you understand it up to the equation 16?
No, up to the 15. Okay, so I'm okay. Okay.
Okay. Now, he said from earlier on, he said the CV, that's the constant volume, the specific capacity, the heat capacity at constant volume, CV, is the same as change in the heat over change in temperature. And now they say it's equal to the first term. So it means change in the internal energy at constant temperature over dt at constant volume. So this is the CV. Because realize this term, the first term you're having here is at constant volume. So at constant volume, which is the CV, is given by this. Because if you differentiate the V over dt, we are going to get 0. Why? Because the volume is constant, so there will be no change in volume. Is it understood? Is the equation 16 understood?
Yes, sir.
Okay. Now, if that's the case, then let's go to the specific heat of. Let's go to the specific heat at constant pressure, the CP. Now, CP is also the same as the K over the T, but this time at constant pressure. Okay. Now, if you look at the whole term we are having here, you don't have any constant pressure term. So it means you have to do something with all what we are having here to get our CP. So they say CP is also given by the whole term. The whole thing. Okay. But then they differentiate this one with respect to the T at constant pressure. Are we okay?
Kindly go over this part. Say the 17, the 17, is it a constant that whenever you see the Z over the T is equal to 0? Or
Yes, that's for specific the heat capacity at constant volume. Because if there is no change in volume, at the end of the day, we have nothing going to change. So the dV is 0. Since the volume is constant.
okay, then the 18 to
You said?
then continue from the 18, please.
Okay. So from here, that's the same thing we have over here. Okay. I hope you've seen that there's no change. The only change we added to it is that this time around, the change in volume at with respect to the change in temperature, it's happening at a constant pressure. Are you saying that this equation is the same as what you have here? The only difference is that this was not happening at any constant parameter, but then we introduce a constant pressure.
I don't see the case. So which of them is the least? I don't know which one. Say this one is the same like this. I don't see the.
I mean,
Or I can't see
equation
the.
15 and equation 18. There's no change in anything. The only change here is that when you look at equation 15, there was change. We are trying to find the differential of the volume with respect to temperature without holding anything constant. But when it comes to equation 18, we are looking at that same parameter, but this time at a constant pressure. Are you okay now?
Yes, please.
Yes.
Okay. Now, they said the difference in the heat capacity at constant pressure with heat capacity at constant volume gives the expression. So we are trying to find the difference between the constant volume and constant temperature. I'm sorry, constant pressure. So we have Cp minus Cv is equal to, now this second term, because you know the first term is Cv and it's equal to 0. Okay. So if you subtract this, you are going to get equation 19. Are we okay? Okay. Now they said indicating that Cp is greater than Cv for a particular system. The reason is simple. Heat will need to be added when heating at constant pressure than when heating at a constant volume. This is because when heating at constant volume, additional energy will be expected on doing work on the atmosphere as the gas expands. Another useful quantity is the ratio of Cp to Cv, which is called the adiabatic index. So the adiabatic index, which is expressed as the gamma, is given by Cp over Cv. That is the constant heat, the heat capacity at constant pressure over the heat capacity at constant volume. Okay. Now the SI units for heat capacity is joules per Kelvin. That's the heat capacity, you know. Should we refer to heat capacity per mole or mass of a gas, we have to use small c for the latter, known as specific heat capacity, and Cp is equal to Cp over big M. So this, when you see the capital Cp, you are talking about the heat capacity, but when you see small c, you are talking about the specific heat capacities. I hope you are making sense.
Yes, sir.
Okay. So if you want to find a specific heat capacity of a system, it's given by the heat capacity over the mass of that system. Okay, or the mass of the material or any object that you are dealing with. Okay, so that's what you have over here, and that's for the specific capacity at constant volume too. We have it over here as well. Okay. And they said find the heat capacity of an ideal monoatomic gas, and they've solved everything for you, which I will leave you for you to do it yourself. Because when you're talking about monoatomic gas, it means the degree of freedom is what? 1. So you just go ahead and do that. And with this, we've established already the internal energy of an ideal gas. We spoke about that already. So I'll leave this for you to go and do it, read and understand it yourself. Then go to reversibility. The reversibility is nothing more. It's just when there's a change of state, reversing it back to its initial state. That's all what this reversibility talk about. So the laws of physics are reversible, so that if any process is allowed, when the time reverse process can also occur. So when you have a system being going forward, when you reverse it, it has to also hold based on the physics laws. In a reversible process, the system undergoing the process can be returned to its initial conditions along the same path and endpoint. Along this path, the equilibrium state. Okay, a process that does not satisfy these requirements is irreversible. So any system that cannot revert back to its initial condition is said to be irreversible. They said all natural processes are known to be irreversible. Okay. So we move on to the session 6. Let's talk about isothermal and adiabatic expansion. And as you've already established the foundation, so when we talk about isothermal, it happens at a constant temperature. and adiabatic constant pressure as well. Constant heat. So as explained previously for an isothermal process, the work done by the gas on its surrounding as it expands is equal to the heat absorbed by the gas. The expression, the W is equal to negative PdV, represents the correct expression for the work done in its reversible expansion. Hence, the heat absorbed by the gas during an isothermal expansion from volume 1 to volume 2, that's initial to final, of 1 mole of an ideal gas at temperature T is given by equation 28. Okay. So it means all these holes, and this have been established already, that the Q is equal to negative W. So if we want to factorize the W as the PDF, that's where we come to this point. Okay, so the one I was trying to explain earlier on, you have the Q to be negative PW, and you have the W to be what? Negative PdV. So that this negative will cancel the negative out here. I hope it's explained. Okay. Now, from ideal gas equation, we know PV is equal to nRT. Now, we assume the N is equal to 1, so that we have PV is equal to RT. Now, as PV is equal to RT, let's make P the subject, so that P will be equal to RT over V. Then we substitute that RT over V in the P. Yes.
Yes. I'm thinking that negative technically will not just cancel out because it depends on the value of the differentials.
I don't understand.
I mean that the negative I talk about over there that will cancel.
Mm-hmm.
You notice that it remains. So they didn't write any expression where it disappears. So I don't know, equation 30.
Yes. So we realize we are integrating respect to V.
So if
The
you
pressure is constant.
Okay.
The negative is also factorized out.
Okay.
So if it's factorized out, we have negative here already.
Okay.
So that
what about if your differential value becomes positive?
Is it?
If you differentiate, if you find the integral, that integral value there, that PdV, and the value is positive now, with respect to V1 and V2, will that still become positive?
Yes, because if we want to maintain the negative sign here, then means we have to reverse the volume over here. So it will be V2 to V1. But realize it's still maintained. It means we are factorizing the negative out. Okay. Because it's being treated as a constant, -1. And we have -1 here already. So you have -1 times -1 giving us +1.
Okay.
Yes. So in the case where the negative is not factorized out, it affects the limits of the function. Okay, so instead of having V1 to V2, it will be V2 to V1. That's where you say the negative has not been factorized out. But since it's still maintained, it means it has been factorized out.
Okay.
Yes. So here we made P the subject from the ideal gas equation. So you have P to be equal to RT over V. Then we factorize the RT over V in this P expression. So that we have the integral of V1 to V2 of RT over V, then the V. Now the RT is a constant, so you can factorize that out. So that I have RT integral of the V over V. And you and I know that when we are trying to find the integral of a function, the ratio of a function to a differential, then we can express it in terms of length, right? So that the 1 over V dV is the same as length V. So that I have length V2 over V1, which is the same as length V2 minus length V1. I hope you are good. Okay. For an expansion, V2 is greater than V1, and so the Q is greater than 0. The internal energy is constant, but the volume has increased, so that the energy density has decreased. The energy density and the pressure are proportional to one another, hence pressure will also have increased. Okay. Then we go to that of the adiabatic expansion of an ideal gas. Do you understand that of the isothermal? That's this point. Do you understand it?
Yes, please.
Okay. So we go to the adiabatic expansion of an ideal gas. So in adiabatic expansion, there is no flow of it. Hence, we have the Q to be equal to 0. So that from the first law, we say our du is equal to the W because the Q is 0. Also, substituting that, we know that CV is equal to the U over the T. Okay. So that we have our U to be equal to CV dt. Okay. And we also know that our dW is equal to negative dV. So let's try to substitute these parameters in the equation you're having at 35. So that our du will be CV dt, which we have at the left-hand side. And our dW is equal to negative P dV, which is at the right-hand side. I hope you are good. We've not changed anything. Are we good? Please, are we good? Should we move on? Or there is any question?
So the things are continue. I don't know about my
Okay.
other colleague.
Okay. So here, the same thing. Ideal gas, we know our PV is equal to RT. So let's make P the subject just as we did over here. Okay. So P is equal to RT. So let's substitute the RT wherever we see P. So that here we have RT over V dV. From equation 36, we are substituting P to be equal to RT over V in equation 36 so that we get equation 37. I guess there's no confusion. So now let's divide equation 37 by CV. So if you divide equation 37 by dV, you have dt equals RT over V dV times 1 over what? CV. I hope it's clear. Then we also divide through by T again. So that I have 1 over T dt equals, now this T here will cancel the T we are trying to multiply through. So that I have R over CV times 1 over V dV. I hope you are okay. Any confusion?
No, sir. No, sir.
Okay. So equation 38 is also established. Now we are trying to eliminate the differential part of the equation. So what do? We introduce a integral sign, or we integrate the whole system. So that when you integrate the left-hand side, you have the T over T. So integral of the T over the T will give us what? Ln T. So ln T2 over T1, that's the ln of initial minus the final. So you have ln T2 over T1 over. Now R over CV will be treated as constant. So you have RCV, then we have the integral of dV over V, which will also give us ln V2 over V2. Okay. Are we okay?
Yes, please.
Okay. So if that's the case, that means you can divide through by CV, or this whole thing becomes this. This is a constant that has been established already from here. Where is it? Where is it? Where is it? Here. Where is it? Where is it? Where is it? Sorry. Um, I think yes, here. That's P is equal to V plus CR. So this has been established already. So that's what I've
Yes.
been. Yes.
Yeah, please, that part, I don't know if we have already done it or it was the part that you said we should go learn it. That part that you
Yes.
went back.
Yes.
You said we should learn it.
It's the
or
work
it's not already
example
done?
that I gave you. So it's try to establish the relationship between them.
No, but I'm saying that that part, did we go through it
You say I didn't.
or did
Yeah,
we
we
go
didn't
through
go
that
through.
part?
Yeah,
That's why I said that
that's
maybe.
the one I said is the example I said you should read on.
Oh, so
That's
it's not
the
that clear.
example.
Oh. It's not clear. So if you can spell like 2 minutes and it take us, can they take us to it? It will be better. So it's not that clear. Not
No,
something that
it's
you
the
can.
same thing we established from the beginning from here to that point. So we are just trying to make substitution. That's all. Just like what you have been doing. So if you realize that adiabatic process at constant temperature, you have this to be zero, right? You have PV is equal to R, so you make V the subject, you substitute in those expressions. And that's the same thing we are doing. We've not changed anything.
Say,
Yes.
please, at 26,
Uh-huh.
like 25 with the 26.
Uh-huh.
Can you kindly 25 and 26?
If you do this, maybe you'll not finish the course. So, well, anywhere we get to, that's fine. We said the equation, the question, they said it's a monoatomic gas, right? And for monoatomic gas, the degrees of freedom is given by this. That the U is given by this.
Then he
So
said, please,
that,
it's a constant, right? Or it's a formula.
yes, yes. For monoatomic gas is given by this, and diatomic, we have the number of degree of freedoms that for any atomic or for any system we is related to. Yes, that as far as this course is concerned, you are always limited to just a monoatomic system. So the degree of freedom for any internal energy is given by this. So knowing that you just substitute that one in here, you know that the U is equal to this. So that when you substitute the U in there, you just get to the 26. Yeah. So this is established already. It's a constant, you know. So that when you have this expression, you can divide through by CV. And dividing through by CV, you get this. And also we stated that CP over CV is known as gamma. So gamma is equal to 1 plus R over CV, which we have over here. Okay. Now let's make R over CV the subject so that I have gamma minus 1. Okay. Now if you have R minus CV, R minus CV is also explained in equation 39. So it means equation 39, we can substitute the gamma over 1 in there. Please, are you following?
Yes, sir.
Okay. So that here, you know R over CV is equal to gamma minus 1. So from this equation, instead of this R over CV, we are going to substitute gamma minus 1. So that I have ln T2 minus
Say,
T.
please. Say,
Yes.
please, when you are moving, because sometimes the tester is very small, I think that you use the equation number so that we know that we are at equation 40, equation 41, please. But when you move the cursor, I don't see it. Thank you.
Okay. We are saying from equation 39, right? Our R over CV is the same as equation 43. Okay, so in place of the R over CV in equation 39, we are substituting equation 43. So that in equation 39, half ln T2 over T1 is equal to negative into bracket gamma minus 1, then bracket close ln V2 over V1. And that's what we have in equation 45. Exactly.
Yes, please. Yes.
Okay, so if you have this, then this can now become TV exponent gamma minus 1. And I guess you know how you know the gamma minus 1.
Yes, but how it became the power, that is the issue.
Yes, because if it has a ln, right, and we introduce, so this whole thing the same as ln v2 over v1, or in bracket exponent negative gamma minus 1. Do you understand that? You know, if you have ln a exponent 2, it's the same as 2 ln a. You know that?
Okay. Yes.
Yes. So the same thing is what we are doing here. So you have ln into bracket v, then exponent all what we are having here. But now we want to eliminate the negative sign over here. So it means we have the ln v2 over v1. Will not be v2 over v1 again, but v1 over v2.
Oh, okay.
Mr. George, are you here?
So I'm here, but yeah, from 45, I have it changed to the 46.
That's what I'm
Not that
explaining to you. So I want you to get the concept well.
okay. So
You understand to the
maybe if you
45,
can go,
right?
yes, I understand to the 44, 45.
Okay. Now from 45, we want to eliminate the negative in front of the bracket. Okay. So if we want to eliminate the negative in front of the bracket, it means you have to change the v2 over v1 to v1 over v2. Is that understood?
Yes.
These are identities of log. So if that's possible, and we know if you have ln a exponent 2, ln a exponent 2 is the same as what? 2 ln a. Is that true?
Yes.
Okay. If that's true, then it means you can rewrite this as what? Now the ln t, let's try to take the exponential to this point, this one. This is an exponent for the v, right? So this is the same as ln t2 over t1 is equal to ln v1 over v2, or exponent gamma minus 1. That one is true, right? So if that one is true, after that, let's introduce an exponential function, which is e, so that we have e ln t2 over t1 is equal to e ln v2 over v1 exponent gamma minus 1. So that the e, then ln will go away, leaving out just only the t. Is that correct?
Yes, sir. So in that part, how did it change to now when you go to 40? It became TV to the power y minus 1 is equal to constant. Which constant is that? Or that one, whenever you see
No,
TV to
no,
the
no, no,
power
no, no,
y.
no, no. No, it's let's try to understand it. So from here, because the negative affected here, right? If we want to get rid of it, it means when it comes to this side, it's no more a division sign. It's going to multiply. I don't know if you understand what I'm trying to say. If you have ln A over B, right? Let's say A is equal to ln B over C. Is it not the same as A times ln C over B equals to 0? Is that identity, or is that clear? Please, Mr. George, are you following?
I'm here. I'm here. But that part, I don't know if
No,
you
I
can
want
write.
you to.
Oh, we did it a long time ago.
He said,
That I'm trying to understand that question. But maybe you can go on later on. I'll go. But that part is not clear with the 40. Like,
from here, right? The negative
yeah,
sign
only the
here, when
45.
you
How the T. So how the T and then the V. I don't know whether you
multiply.
found the.
So, okay, fine. Let's do it
Yeah,
this way.
maybe some writing will do, or say it's not possible to write it.
I'm not having the
Mm.
writing part. That's why.
Okay. Yeah. So that would have solved this issue.
So from here, we have lane T2 over T1, have V2 over V1, right? But this is affected by a negative. So if the negative is to go through by the lane, it means it's the same as lane T2 over T1 times lane V2 over V1. And this one is to the exponent of what we have in the bracket over here. Okay. So that when you find the exponential of all the terms over there, we have exponents lane T2 over T1 times exponent lane V2 over V1 exponent gamma minus 1. And now because the integration was not a definite one, it means we introduce a constant so that the integral of this one and that one will have a certain constant, which is given by this. I don't know if it's making sense now because the
So
V
it
factor.
means that so it means that lane T2 over T1, when you integrate, you get T, you get capital T, right?
Yes, not that you are integrating, you don't integrate. You just apply exponential function to everything you have here. So to be
Okay,
e
so that's what we.
exponent ln t2 over t1. So
So
that
when you
the
do that, you
exponential
get.
will cancel the lane. Is it clear now?
So we beg, yes, if this one contains a lot of proofs, sometimes it will help if you can write small. But this one, most of the things they are proofs. They are not even ready. I think if you are
Okay.
writing, this would have solved this a long time ago.
Okay. Right now, let's go for our 10 minutes break. Let me try to write it down, take a picture of it, and send it in your group for you to understand it.
I think it will be better. It will
Okay.
be.
Then let me use the 10 minutes break to do that and send it to you guys. Okay.
Thank you very much.
All right. So we come back in 9:10.
Hello. I can't hear then. What is going on?
Me too. I can't hear anything, so I'm also there waiting. It's happened. I went off, so when I came, I'm not hearing anything.
Hey, hello.
Hello.
Hello. Hello. Hello.
Yes, hello.
Yeah. Can we get back now?
Yes, sir.
Okay. So from what we were doing, okay. I guess you can see it now.
Yes, please.
Okay. So from where the confusion was, we said ln T2 over T1 is equal to negative R CV, then ln V2 over V1. And also stated that R over CV is equal to gamma minus 1. So that we have ln T2 over T1 is equal to negative gamma minus 1. Then ln V2 over V1. So just substituting this in this equation. Okay. Now, we know when we are doing lane, if you have lane A or lane A exponent to the same as 2 lane A. So it means this expansion or this expression you're having over here, the same as what we have here. So that you have this as the exponent of the V1 on V2. Okay. Is it clear?
Yes, sir.
Okay. Now, if that is the case, now let's try to apply exponential function, that e, to all sides of the expression. So that when we do that, we have e exponent or e ln T2 over T1 must be equal to, now, because we have negative 1 here, in lane or in logarithm, if we have a negative sign, the same as division. So that I have 1 divided by everything we have over here. So you have 1 over, now you applied lane here, so you apply, you apply exponential function here. Meaning you can apply exponential function here as well. So that I have e exponent ln T2 over T1 equals 1 over e ln V2 over V1, and it's to the power of gamma minus 1. So that the e and the ln will just cancel out, leaving us the T2 over T1, which we have over here. And the same thing applies here. This will cancel this, giving us V2 over V1 exponent gamma minus 1 over here. Are we making sense?
Yes, please.
Okay. If that's the case, let's let T2 over T1, since it's the same as temperature, let's call it T. And V2 over V, let's call it V. So that we have T is equal to 1 over V exponent gamma minus 1. So that we have what we have over here. Okay. Now taking everything to our left hand side, we have T times V exponent gamma minus 1 equals to 1. And that's what was done in the book. I hope it's clear now.
Yeah, very clear.
Mr. George, is he here or is not yet back from break?
So, I'm here. It's okay. It's clear. It's clear.
It's clear now.
Yes, sir.
Okay. Okay. And that's why we had this. And instead of 1, they said constant, because we are dealing with whatever it change at a constant parameter. So if they say constant, it's nothing more, nothing. They are just trying to tell that anytime that you are doing that, it's respect to some constant variable or constant parameter. I hope it's clear. Okay. So from there, we have our PV to a certain constant graph. And this is what is being done over here. So they said They said figure 1 shows isotherms, that's isothermal graphs, isotherms lines of constant temperature. How should we follow in an isothermal expansion and adiabat lines flowed by the adiabatic expansion, the fluid cannot enter or leave the system. For an ideal gas, for an ideal gas on a graph of pressure against volume, at each point, the adiabats have a steeper gradient than the isotherms. So if you look at these graphs, they said always the adiabats has a steeper gradient as compared to that of the isothermal lines. Okay, so the ones that go this way are that of the isotherm, and the one that comes downwards is the adiabats. I hope it's clear. Okay. With this, I think it's nothing for you to worry your head on. I won't really struggle. So we go to the adiabatic atmosphere. The adiabatic atmosphere. The hydrostatic equation expresses the additional pressure due to a thickness, that's the Z of atmosphere with density rho, and it's expressed as. So when we want to find the pressure, right, at a very system of thickness, let's say the Z, with an atmosphere of density rho, then it's given by what we are seeing over here. So that we have the P is equal to rho G dz, rho G dz. Since P is equal to nkBT, now the pressure you are having here is respect to the moles, the Boltzmann constant, and the temperature. And that of the pressure, the density is given by the moles and the mass. Where M is the mass of 1 mole. We can rewrite this expression, the pressure as this. We have MP over KBT, where the rho is the density, the M is the mass, the P is the pressure, the KB is the Boltzmann constant, and the T is the temperature. And hence, the P over the Z will be given us question 49. Are we clear? Is it clear? Do you understand? Do you understand now to equation 49?
Yes.
Okay.
Yeah.
So they just yes.
The P is already predetermined formula that we are just substituting into the preamble.
We look at this general expression, right? And we know density is this, so we substitute the density expression over here. Right. Then we divide through by the dz, so that we have the P over dz is equal to the density. Now the density is expressed as this. Okay. So instead of this rho, we put MP over KPT. So that we have the P over dz is equal to rho G. From this equation, we are dividing through by dz. So that I have the P over dz is equal to rho G. Okay, and rho G, now we are substituting the rho of this expression into that one over here. So that we have mgp over kbt. Mr. George, is it okay now?
Yes.
Okay, so the equation 49 is just substituting this in this equation and dividing through by this. Now they say which implies that T dp over P is equal to mg dz over kb. Okay, now they multiply through by the T and also they divided through by P. So that you have the P at one side and now the T also at the side where you have the P. So that if we integrate the left-hand side, you have T ln P. I hope it's clear. If you integrate the left-hand side, you have T ln P. Okay. For an isothermal atmosphere, T is a constant. Yes, because when we talk about isothermal process, we have anything happening at constant temperature. This assumes that the whole atmosphere is at a uniform temperature and is very unrealistic.
Oh,
Much,
sir,
yes.
please. So sorry for, I don't know. Maybe you have said it, but me, I didn't hear. Why the negative introduction of negative?
Which one?
Question 50,
50.
49, 50. Yes,
Okay.
49, 50. There's negative in the equation there.
Yes. I think there shouldn't be any negative there. There's no negative there. It's supposed to be positive because you have the P over the Z giving us this. And if density is this, so there's no negative over there. I think it was a mistake.
Thank you, Doc.
So said,
Yes.
please, couldn't it also be by virtue of the fact that you integrated, maybe the integration?
No, it's not with respect to that because if you are integrating it, it's the P with respect to P, that one is positive. It's where is the inverse, that's where negative comes in. Okay. A much better approximation does each parcel of air does not exchange it with its surrounding.
Yes. Yeah, okay. If I may also ask, so say, in the adiabatic atmosphere is the thickness. This is if additional pressure due to thickness of the Z of the atmosphere with density P. So, are there any relation between the pressure and the density? That's why they are indicating that maybe as you increase the pressure, the density reduces. That's why they introduce a negative there. Or could that also be the case?
Mm, okay, in natural sense, you realize in the atmosphere, if you are going upwards, temperature has to increase, right? Do you understand that basics?
Yes.
Yes, but that's not the case.
Okay.
As you are going further, then the temperature reduces. So maybe I don't know. Maybe that's the matter of that one. So I can't relate about for now. But I will do that and get back maybe next week.
Okay.
Okay.
Okay. Thank you.
Yeah.
So Yusuf,
Yes, madam.
please, can you get us last year's price question? Because the way the formula and the thing, I don't know how the question is will be.
Um, I I will find out. I'll try and see if I'll get it.
So we'll be very grateful. We'll be very grateful if you can help us
Try
with that.
try harder. Don't try small. Try harder to get it.
Then talk to Dr. Peter. I mean, you know Dr. Peter, right? The coordinator.
Yes, but we've not been. I've not been talking to him.
He has never taught us before. So since you are there with him, maybe you get it from him and just put it on our page. We can download it. We are not asking for the maybe soft copy. Soft copy will do, or even screenshot of it will be okay. Thank you.
The thing is, he's also part of the people on that platform. Okay. So I don't know if you guys can insist on that in the group or something.
So we will be
Because
asking
if
to talk about. We will not get it.
Eh, they've
because
never
if
given it out before.
Any, yeah,
We have
we've been
requested
asking
several.
several.
They've never. So this one, we are asking that you should make us a favor. If you can get it for us, you do it privately. We'll be very grateful. Because of where we are coming to UCC is a private. Sometimes we get it, but it's maybe a day to the exam, or sometimes an hour to the exam. So you don't know exactly where you should learn more. That is why where you should learn more. Sometimes you end up learning areas that maybe we didn't know this is how the questions will be. That's why we are saying that if you can, this one is not like a report that you are
no,
giving
I
us
get you.
past the
I
question
get
to go
you.
and learn.
I get you because past question is just to make us, let's say, a standard when you are reading.
Yeah.
But then, because most often some of the questions are being repeated, that's why they don't really like it to be going out more often. And the second point is also that even me that I'm taking the course, I have no idea of the questions that will be coming.
Yeah, that is one thing.
Yes. So there are some things we know for sure. If you say you've done this course, you need to know. And that's are the things that sometimes we just pay more attention to. So that at least as far as the course is concerned, for a standard exams or a standard quiz, we need to see those kind of things in. That's why sometimes some of the things are there. We say, don't stress yourself, or we just don't waste much time on it. Not that we know that we are not going to, we are the ones setting the exam, so nothing will come from there. But because as far as we've done that course, those things really doesn't matter. But some things are very, very much important that you need to take a look at. So that's the main issue or the main point. That's why you've been saying that.
So, but were you the one who took the last year people, the last year switch?
Last year switch, I,
Yeah.
I I just took you guys through electricity and magnetism, and I
No,
gave you
that
guys
when
tutorials.
Sir Festus was out of the town.
Yes, but the tutorials I gave you, at least you saw at 70% of those things in your papers. Or
Oh yes. Now I'm talking about last year batch, not ours, not our last semester.
like last year batches in thermal physics.
Yes, please.
Yes.
Like those questions is their end of sem question is what you're talking about.
Yes, that one I wasn't the one who set it. That's what I'm trying to say.
Okay.
Yeah. Just that it was brought to me, and that was
You
how
have
I
read
got.
it. Please
Okay.
try for us. You have read it. Thank you. We know
Sir, please,
you.
a
We are
tutorial
thanking you in
question.
advance. We are thanking you in advance, believing that you will do it. Thank you.
Mr. John, is this a request or is
It's a request by
It's a request, which I believe that you will do.
request.
So
a
we thank
request
you.
is a thanks?
Sir, please, and tutorial questions as well.
Don't worry, I will see what I can do. I'll talk to him only if you will just hear me out. I'll try my possible best to talk to him for you guys.
Okay.
He was even supposed to be on the meeting today. He said he had a message for you guys. I don't know why he didn't join though. Actually,
Can you remind him? Maybe he has forgotten.
let's see. Maybe after the meeting, I'll call him because you guys we are supposed to even end now and continue tomorrow. But then last week we did that and no one came on the Sunday class. I don't know why.
So for me
No,
last
we
Sunday
year
we
I
join
was
you.
There was no one there. I think I contacted some two people and they were like they forgot. You want a constant reminder, right?
But we join
was
later. I think you had a class, oh.
No,
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 it
no.
was
We
Monday that we
agreed
did.
on 7:30 p.m. Is it 7 p.m.? Yes, 7 p.m. But no one was online.
Oh, okay.
Some of us
Yeah.
waited, but nothing.
So I
Oh,
think what
really?
happened, even on Monday's phone, on Monday that we did, I was doing something and I said, let me check. When I checked, Festus was there waiting for us. At least, maybe I thought maybe he can even contact the course rep and then a gentle reminder. But he was there, he's been there for about 30 minutes. Then I have to, because sir, are you still waiting for? I said, yes. Before I call my colleague. So I think that sometimes it's not our, it is oversight. Even today, I got here 7 o'clock, and from 7 o'clock to 7:20, no one was there. So when I get saying that it will be on and off. So maybe if you can get somebody that you can relay the message, I'm ready. We'll quickly join. We see most of us are family members. I think that's the problem. Sorry, sir.
Okay. So should you do that today too, or you should just go ahead?
Me, I'll be grateful, but I don't know about my colleague because from what we
so
have
today
gotten, I would
this
love
evening
to
or
go through
when?
so that
Tomorrow
I
evening.
have to go through
Okay.
so that when we meet, I can identify those areas. That's when I was learning and I got here. But if you are to end everything now, going back because next week will be face to face. That is from our color. Next week will be face to face. So some of us will be going to our various centers. So I don't know if it is okay.
Ah, but next week is the last week.
Yeah,
Oh.
No, next week is the last week.
yes, usually it's face to face, but others will join online. But if it's not online center, we have to go back to our face to face. That's what I think.
Oh, okay.
Sir,
Then for me, I don't know. I would like for us to end here so that we continue tomorrow, 7 p.m. to 9 p.m.
Okay, so tomorrow,
but
7 p.m.
sir,
to 9 p.m. I will.
Yes.
please, I don't know if you are engaged elsewhere. I'll be grateful if you continue a bit before you stop. At least as to 10 o'clock, then continue tomorrow. 7.
Okay. I have another class. That's why
Okay.
I
Okay.
spoke
All
to.
right.
Okay, let's see.
We can do it tomorrow.
Let's finish. Let's finish with this one. I think it's end over here. So let's just finish with this one. Okay.
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 And then one thing that is that normally the exercises and each this thing when there's exercise, that is what they normally bring them. So at times, if there are some exercises, you try and solve it with that.
Okay. We will see how best we can do that because we have to finish the whole thing before we come to the exercises. And what I feel is when the basics is strong or when you understand the concepts, the exercise becomes something you'll be able to do it. And one thing is also you don't always have to chew and pour for me. You don't always have to chew and pour. If you understand it, you can put it in your own words, but you should have the main concept and you are good to go.
Okay.
Sure.
Okay.
So does it apply to the proofs? Because the proof here, if you don't chew and pour,
The proof is not chew and pour, it's substitution. The proofs they are not chew and pour. It's just a matter of knowing. For example, this whole proves that we are doing is based on the first law. Okay, so the U is equal to the W plus the Q. So knowing that, just change your subject, then you just substitute. Simple. Mm. But then if you can put it in a way that you think it's understandable, you are right. Why not? You have two ways of killing a cat, provided you can explain your terms. That's it. You are good to go. All right. So for an isothermal atmosphere, T is constant. This assumes that the whole atmosphere is at a uniform temperature and is very unrealistic. Yes, so when you go into the atmosphere, this equation is telling us that the temperature in the atmosphere is constant, which is never true because you realize when you are going upper, the temperature has to be increasing. By go to a certain region, it will be reducing, and even in the spatial spatial analysis, it's also not the same because you can see the sun shining very high or very the intensity of the sun will be very high here. By go to other region, it will be very low. Okay, so even in the atmosphere, the temperature is not uniformly distributed, and that's why they are saying it's unrealistic. So a very much better approximation does each parcel of air does not exchange it with its surrounded. It implies that it's a parcel of air. If the parcel of air rises, it expands adiabatically. So if the air rises in the atmosphere, then means the atmosphere expands adiabatically. We can now solve equation 50 by recalling that the P exponent 1 minus gamma and T gamma is a constant as this. So that we substitute the P and the T terms in this expression. Okay. Because I hope you are following or there is confusion.
We are following, but just that I don't know when the equation will end. So now we are 52. I don't know when it's going to end.
Oh, it's ending just here. It's end as 53, then we are good.
December. Question 3.
Oh no, it's if a question is being asked, you're not going to do all this. So, for example, they can say show that for a specific heat at constant volume, CV is given by this. So if you know that, it's just maybe from equation 1 to equation 3, then you are done. So that one you can just say from the first law of thermodynamics, which is the U is equal to the the W plus the Q. Then you go ahead and put in the parameters that is constant, the one that is changing. Then you are done. Sometimes by just 2 or 3 steps, then you are done. Yeah, but it's deriving of so many equations. That's why they placed that it's up to that equation 53. So no one will ask you to prove from equation 1 to 53. Add a 500. That.
Stuff. This is Subekunipa.
Okay. So now from equation 51, then we come back to our equation of making the T, the Z the subject, which will give us equation 52. And that will be the end of the whole thing. I hope you are good. It's not anything strange. It's not anything strange. It's what we've just done, and we just go to this last point.
Okay.
All right. So I think our next meeting, which is tomorrow, we be starting with equation unit 4. Okay, we'll be doing unit 4. Then maybe our last meeting.
Thank you very
I
much.
don't know. We'll do the unit 5 and 6. All right. Any question?
You don't even know the question you want to ask.
Don't worry, you just go sit down, go over again. Maybe by tomorrow the time we'll meet, you come out with some things that you don't understand and we solve them together. Okay. But then I'll try and see if I can get the last question for you guys then. We try hands on. All right. Doc. Dr. Peter.
Good morning.
Good morning.
Good morning, Doc.
How are you doing?
We are
We are doing
Okay.
We are doing good.
All right. I'm good. I want to believe everything is going on well.
Yes, sir.
yes, sir.
Good. We are on the field of thermodynamics. That's great. As I said at the beginning, this course very good. Okay. We want to get some issues on the page. Last time I heard they complain about the thing on the slide. And the information you guys had, right? Hello.
Line is breaking.
I'm saying that. Can you hear me now?
Yes.
Yes, sir.
Okay.
Can you guys hear me? I'm saying that with electronics, I heard some comments on the page. Oh, I saw. Let me put that way. Yeah, so wait. Whose microphone is on? Benjamin. All right. So basically, you were like, what were thoughts and the question that came? We're not in tangents, right? Is that what you guys were saying?
Yes, sir.
Seriously, are you sure?
Sir, to be frank with you,
Uh-huh.
we were concentrating on the slide, but the slide were not helping us. And then the model, we didn't concentrate on the model, and the things were coming, the detailed things were coming from the model. So
Yes.
the electronic, it was bomb for us.
It will be bomb. So basically, what with code system, okay, right? When you are giving the model, as you can see, Yusuf is doing, everything is going to come from the model.
Your line is breaking. So we can't hear anything. Dr. Peter, please, your line is breaking.
So when slice are the slice
So please, we can't hear you at all.
Please, can I hear okay? We can't hear.
So your line is not good at all. We can't hear anything.
I get my point. The best way to go.
So
Slice
please,
are
all that you said,
how you can even
we didn't hear. Your line was cut.
right now.
All that
Hello,
you
can
said.
you hear me now?
The line, we can hear you now, but what you said previously, we didn't hear anything, please.
Okay. So what I'm trying to say is that when it comes to the slides, okay, slides are just bullet points. All right, they are just bullet points, a summary of what is in the book. All right. So anybody who uses slides to teach, I want to believe some of you are also teachers, right?
Yes.
Yes.
Dog. That's dog.
Yes. So you also make slides. Good. So when you make slides, it's a summary of what you want to go and teach. All right. So when you pick the bullet points, then you explain. When you pick the points, then you explain further. You say more illustration, more things. Is that okay? So slides.
Dr. Peter's network went off, I guess.
Yeah, I think you'll get.
Hello.
Yeah.
Yes. He said his network is not helping me. You just finished talking. His network is not helping him, but then he will join us tomorrow, 7 p.m. Then he just give the information he wants to give. Okay.
Okay. Thank you.
So we meet tomorrow, 7 p.m. Please, I'm begging you. When it's
The
7
same
p.m.,
thing.
just
The
yeah,
same
the
thing.
same link. The same link.
We'll be reminding ourselves.
Okay. Thank you for your time
Okay.
and enjoy the rest of your.
Thank you so much.
Thank you too.
Thank you.
Colleagues, I think when doctor join us tomorrow, we have to ask him to give us some of the area for quiz. Let's say quiz 1, because the course is not easy.
Exactly.
The course is not easy to learn everything.
Yeah.
Oh, I lie. The electronics. What happened? I lie. What I said, is it wrong?
Oh,
Yes,
madam, you were right.
Maybe
You were right.
you say the speed.
It's not wrong.
Okay.
you're right. That was what happened. You see that on our final day, I don't know if you were there, it was online. And I was requesting, said, take us through, said, he said, oh, no, no. Because of what he said, I didn't learn that part. Because if a teacher is telling you leave that portion, what to do? Oh, it is right.
That is why this when he's teaching the other one, I've been insisting that you should use the questions in the manual to give it to us.
Yes,
So
because
if it is
even
here,
though
whoever is teaching, I normally compare it with the manual and tell him to give us the solve the questions in the manual with us because that is what they have been taking.
Mm-hmm.
yes, yes, that was true.
So
That
we
was
should all insist on it. Whenever he finishes and there's a question there, we should try for him to let us know how it is being solved. Because until the my do one when I sign bomb. So me, I don't want to download his slide. Because I don't want to download his slide. Not to even learn it. The same
Also, I
happened
mean,
in general physics.
also may I solve all the questions.
Ah,
If
general
you
physics
have,
that is what happened. And now some of us are going to write general physics again. So that this
Okay.
way the many are
My opinion is also that, you see, in as much as what we are saying is valid, you should also look at the realistic aspect of it. If we in a lecture want to go through all the questions that are in the sessions, there's a higher possibility that we will not even reach, a considerable level of what's the name, like unit. We may end up reaching maybe unit 3 or 4, and then that's it. So yes, we should put our concerns within some measurable or attainable, measures, because otherwise we would be solving questions, and if you are not lucky, we will not even reach anywhere. So that is
no,
also my
we are
that
not
question.
saying we should solve all, I understand it, so not to solve all the questions in the manual for that one, it can't happen. But one thing I want to draw his attention is that most of his attention should be on the manual because
Yes,
his slides are
that's
plenty
valid.
of
So
the
I
manual.
think a colleague was saying that we should make sure we solve all the questions, and that is where my
Okay, okay,
my response was coming from. Yeah.
okay, okay.
okay. So, colleague, thank you very much, madam. Please,
If anybody is having
tomorrow.
the past question, they should bring it out. Oh yeah, more past question. If you know the colleagues of the last year people, you should contact them. No one do questions in be my end. Oh yeah, questions not be late. Oh now so yeah, what about?
And that one too, let me add
Sometimes
that
they bring it like I don't know.
I would suggest that if somebody gets a question like that, instead of putting it on the main platform where maybe our lecturers are, because once they see that we are seeing the questions, they may likely also change it.
Change it. So you should bring it to our study group. That is the one culture has created. For that part, we are all there, so they should bring it over there. So please, those who know those that have completed last year, they should contact them and then take the questions for us. We are begging. So
Okay,
please,
thank you.
no
So,
submission
so
about where going.
okay, madam. So tomorrow time for us. When it is time, kindly relay the information here, please.
Okay, I'll do that. For me, last week I didn't join at all. I went somewhere, so I didn't know anything
You
of it.
didn't come. The lesson didn't because no one was there. Because no one was there, he didn't even teach us. I think he left. It was rather
Oh,
on Monday that I saw Sir Festus there, and then I told the class that he was waiting for us.
okay. Even
So
that one,
yes,
cry said that he has sent me the this thing, but I didn't know. So somebody drew my attention that he was teaching, and I said the whole of the weekend I wasn't part of the lectures. I didn't know what happened. So tomorrow I'll remind you
uh,
people. Okay,
okay, thank you.
you're welcome. Bye bye.
Anefi, Anefi, Ojo Anefi, dey here, Emmanuel. Solomon, if you are here, call me. Call me.